Modern speech denoising systems are often trained to directly minimize the waveform distance between a noisy speech waveform and a clean speech target. The rise of high-performing deep neural network sound recognition systems, however, has raised the possibility of using learned representations as a feature space in which to measure distances between sounds. Such networks have generated great interest as models of human hearing, and apparent similarities between learned representations in networks and in the brain suggest that deep features may serve as useful perceptual metrics. By collecting the activations of a trained network to two sounds, and then measuring distance in this deep feature space, a neural network can serve as a loss function for a speech denoising system in place of a more traditional waveform-based loss. Deep feature losses for denoising were previously proposed, but were characterized only for high SNR stimuli, only use features from a single networking task, and were not directly compared to simpler approaches. It thus remains unclear, do deep features actually improve upon simpler approaches, and what choices in feature training produce the best results? Here we make those direct comparisons. We trained wave unit audio transforms to do speech denoising with a variety of different loss functions. As a baseline, we used a waveform reconstruction loss. We also used deep feature losses derived from multiple networks optimized for different auditory tasks. And as a simple alternative, we used a subband reconstruction loss from a one-layer cochlear filter bank. To evaluate models, human listeners rated the naturalness of audio processed by each of our trained transforms. Average ratings are plotted here as a function of the SNR of the unprocessed input. Consistent with previous work, deep feature-based loss functions produce better denoising than waveform-based loss functions. And we found that this benefit is specific to learned deep features. Simply using random network features produces much worse denoising. Interestingly, however, the same benefit could be achieved with a much simpler loss function derived from a one-layer cochlear filter bank, which requires no learned features. We next asked whether the effectiveness of the cochlear model loss function depended on the filter bank's frequency tuning, which was designed to match that of the human ear. We found that reversing the frequency dependence of filter bandwidths, such that filters are broad at low frequencies and narrow at high frequencies, produced worse denoising performance. Closely aligning the frequency tuning of the filter bank to that of the human ear is not essential, however. Linearly spaced filters work just as well as those modeled on the human ear, suggesting that good denoising is possible as long as the filter bank is fairly reasonable. In conclusion, we found that audio transforms trained to reconstruct deep feature representations of clean speech produce better denoising than transforms trained to reconstruct clean speech directly. However, a similar benefit was obtained using simple one-layer auditory filter banks, suggesting the importance of multi-channel over complete representations rather than learned features per se.